Hi, good morning. How's the projects coming along? I hope it's all fine, right? Yeah.
Question on the paper that you want. I mean, are we going to be limited to 6 pages on
Yeah,
this?
yeah.
So you don't necessarily want the 6 different sections or 8 different sections like most research papers seem to show, or do you?
I still want it to look like a
brief.
paper, yeah. If you absolutely have to have something which is not in there, you can add it as appendix kind of stuff. But you ought to be able to explain what you did in 6 pages, right? And follow the guidelines, right? Because most of you, I'm guessing, want to write papers, and you done the same issue all the time. So very, very rarely do you, like if the page limit is 14 pages, very rarely do you write a paper in 9 pages, right? Even if that's all the material you have, you get killed because people assume that you don't have enough to say, kind of thing. So you always have to worry about these stuff. And how many of you written papers for conferences already? Very few. One of the things you end up learning is they give you style sheets, and then you kind of want to get like a few millimeters more, so you kind of make the pictures that much smaller, and you spend a lot of time trying to change the sentences so that so if you have this one, the way to get more space is to get rid of these two. So you spend like half an hour trying to change this sentence so that these two words go away. So you either end up doing like server to SVR or go through your English knowledge to make sure that this can fit into 3 lines, so you can get this one extra line which can be a squish kind of thing. So I hope 6 pages ought to be fine, because you only had like a couple of weeks to work on this project, right? So are there any other concerns about where we are so far? So all this stuff. So if you look at our undergrad OS that we taught, many of you haven't taken the undergrad here, but the undergrad OS typically would talk about memory, processes, synchronization, and file systems. So that's where they kind of stop. And the next module, we're going to go to distributed systems. And again, it's a very brief introduction. The idea here is some of the stuff so many of the things that we studied about, the file systems especially, we rarely use local file systems. I mean, we use distributed file systems all the time. So I want to introduce some concepts of distributed systems. This is by no means, definitive of all the stuff. I mean, we have our own distributed systems class, but this is a pretty vast topic, right? So I want to focus it purely on distributed systems for file storage and all those things, because it kind of extends what we talked about in terms of file systems, buffers and caches, and move things around to not truly distributed, but sort of networked. I mean, especially like NFS is network file systems, where you just move the file storage away from where the client is, but not necessarily really make it to distributed where it's all over the place, right? So it's not going too much in, but it introduced some of the interesting concepts, right? And we use that as a way to learn some of these concepts of stateless servers and all those things. The other reason for studying this is, the hope is if you need to have a working knowledge of operating system for anything that you do, right? And since most of you will be using computers in a distributed file system setting, you use AFS and stuff, you need to understand how AFS works. So you can, the way AFS or NFS works affects what you can see as a file, right? How many of you know how AFS and NFS work, the consistency, what kind of stuff you would get? How many of you understand how a file system works? What's the consistency they get from file systems? You have to answer yes, because you're supposed to have known it from undergrad, right? Meaning, what happens when you write a program saying open, write, close, whatever, right? Right? I mean, file system normally you do open, read, write, and then close, right? So what happens when you, let's say, open a file, write, and then before you got to a close, you fail? What do you expect will happen? What happens if you open a file, do write, and then another process opens a file and write, right? What do you expect to see on the file, right?
Well, you're sort of introducing two different situations.
Yeah.
I mean, in a crash, I think most people would expect some form of recovery. Whether it's going back to the beginning of the file or something like that.
The first one,
Yeah.
right? So when you open a file, you do some read operations are trivial, right? Read operations shouldn't change anything. Let's look at write, right? Open a file, do a couple of writes, and then before you do a close, it crashes. What do you expect would be the case on the file?
Some form of recovery has to be put into place. Either you're going to lose all the work you did and it'll roll you back to the beginning of the file, or if you somehow had transactional-based recovery, you would recover to the last write.
You mean at the application level?
Well, I was saying at the system level.
Okay.
Without.
But like in a current system, right? Like a Windows or Linux or Unix variants, right? What do you expect will happen? Yeah.
The data may not be consistent. The system may start, but you may not have the complete file. Or
So what are the possibilities you can have?
you could corrupt the file system, or you could have the file system in an okay state in terms of the metadata, but the file could be corrupt.
What do you mean by corrupt?
Unreadable by the application that wrote it.
No, it's important to understand what it means, right? So what do you mean it's not unreadable?
A complete, the atomic transaction initiated by the application wasn't successfully completed on disk.
So you can have partial contents, which may make your application fail, right? So I think what may happen is your file may be 0 blocks, right? So something which may happen is your file may not even survive, right? If your metadata was never returned, meaning your directory was never pointed to the file, if that didn't go through, then your file would be gone. So if you go back to the directory, your file will not be there, right? If the metadata went through, because that's one of the reasons why you log the metadata, then you have the metadata. Now the question is, what happens to the file data blocks, right? So it might have been the case that no blocks got returned, no data blocks got returned that could be recovered. That means you get a 0-byte file, right? Or it might have been returned up to some point, and depending on how the scenario is, you may get a partial file, right? Which may or may not be acceptable to you, and but so it will not be corrupted in the sense that it will not have contents that you never wrote, right? That's what I was trying to get to. So you will never see a file which you didn't write. You should never see, right? I mean, if the system that you're using is working normally, you will never see the data changed into something that you never wrote, but it may have partial of it, so your program may crash, right? So you're supposed to know that. So when you write applications, you have to be able to deal with those, right? Meaning when you open a file, you have to assume that whatever you wrote before may be 0 bytes, may be partial, and be able to recover from that. How many of you, when you write programs, do that? When you do a read of a file that you wrote, you do a check to make sure that whatever you wrote is what you think it should be. I suspect most of us don't, right? Especially for course projects, we don't, right? But the point of the class is you have to know, because if you're doing something for real, for your research or what have you, you have to understand what might happen, right? So the key here is if you have to use computers for all your work, I suspect, right? So you have to be able to kind of guess what will happen and be able to recover from those. You have to know what will not happen. You have to know what might happen, because there's certain possibilities. And you have to understand why those happen. And if it matters to you, you should be able to manipulate some things to make these things happen. So if you're really worried about consistency, you would have to essentially do a write-through, right? You have to make sure that every write writes all the way to the disk, in which case your performance will be really, really awful. Like we talked about in the last lecture, it could be 100 times slower because you're writing everything to disk, and that's a trade-off, right? There's no magic bullet here. The more I keep in the buffer, the more speed I get. But the more I have to write to the disk, more consistency I get, but performance suffers, right? And what we're trying to look here is not much different from that concept. It just, the notion here is we're using distributed system. So now the one who writes the stuff, the client and the server are separate. They're separated by some distance. right? That naturally adds some time to it, right? So whatever you could do on the local system is no longer possible, right? It takes a few seconds, few milliseconds to send some update to the client, to the server. So even if you did the same thing that you did on a typical machine, the time to send a message to the server adds some cost to it. So how does that affect what you do, right? So today we start with one of the file systems which is very popular, which is what we'll use in the lab, lab for the where you run some of your experiments, right? Which is the NFS, right? NFS has been around for a long time. NFS has been maligned by people as not good, and I think mostly because people don't understand what it's designed for and what it's supposed to do, right? And you'll see NFS cannot do certain things. NFS is good for some things, and once you understand that, NFS policy is really what it should be, right? The goal of this paper is they look at NFS, they look at Sprite, which is another system, another distributed system, which is on the continuum from sort of like NFS to AFS kind of thing, and they say you can get some of the benefits of Sprite. Sprite is faster than NFS, right? So you want to get some of those benefits into NFS. So they're building a Spritely NFS, which is NFS with the additions that they learned from Sprite, and that's the goal. And they built this, and they get good performance, right? But our goal here is to understand what those changes are, and one of the things about operating system is nothing comes free, right? So Spritely NFS gets good performance at the added cost of other things, which we'll see, right? So in general, the problem of distributed storage or distributed in any of the systems is the notion of maintaining caches. Now there are two caches, whereas in a single system you had a buffer cache or what have you. Now you have a cache on the client and the server, right? So the problem here is the cache on the server is trivial. It's what it was, let's say, before. The problem with the client cache is if you have a cache on the client, then the cache consistency protocol will have to work globally, right? Cache consistency protocol means that if something has to be invalidated, it has to be done globally, right? So the idea here is if there's a block that all of you cached, right? And then one of you modifies that block, which means that the block is now modified. So at the server, I know this block is modified, right? That means now all the things that you have cached is inconsistent, right? You're having the older data than what he has. So I have the latest data. He has latest data. All of you have a old data, right? So I have to somehow tell you. So there's no clear solution of what has to happen, right? The simple solution is for me to send a message to you to say invalidate everything, right? But then of course there's a performance loss, so we play tricks over there, right? The other thing is he may not want to tell me that he wrote something right away because he may be collecting something. So he may not tell me exactly. So it may be the case that he has the most latest information. I have a slightly older information. He has slightly older information. And we do all this stuff to get good performance, but you as a user have to know the stuff because you have to know what you can trust and what you cannot trust, and that's the reason why we read this stuff, right? And then there's other notions of what do we want the granularity of these things to be, right? You want it to be as a whole file or a block based, right? So the good thing is if you do a whole file, then we only operate on a whole file basis. That may make some of your these consistency policies simpler. We'll see AFS, which follows a whole file in the next lecture. If you use a block based, then even on a single file, if he's modifying a particular block which none of you cared, then you may get good performance, right? The flip side is now you have to have more state. Now you have to keep track of all this stuff, right? Rather than saying you're both sharing the same file, now I have to keep track that you're modifying this block, you're modifying this block. So there's more state. So each one of them has their benefits, and NFS is a block-based model, right? The other notion is the stateful versus stateless, which is primarily what they deal with the Spritely NFS, right? So the idea here is all these protocols are running, all these consistency protocols, all this stuff are happening. The challenge is who should be responsible for doing this, right? You can either make the client responsible for everything, and as we'll see, that simplifies everything, right? The server has no idea what you're talking about. Server only does what you want it to do, which means that you have to tell the server everything. It doesn't remember anything at all about who you are. So every time you have to say something, you have to ask the server. You have to say, if you want to read 2 blocks of the same file, every time you have to say which file you want to open and all your credentials to open that file, right? So in that model, the server has nothing to maintain. So the server can be very simple because it doesn't do anything. It becomes sort of like a web server. It basically gets your request and it acts on that request and gives a solution back to you, right? But so it makes it very simple. But as you'll see in this paper, that adds more complications, right? You don't get the performance that you would really like because the server has no idea who's doing what, right? So the server has no idea how many people have opened the file. The server has no idea who's modifying or what have you. So it cannot implement any consistency protocol which could do anything smarter, right? So you as a client are opening a file. I have no idea a concept called file. In like NFS, there is no notion of a file open. So you do open, which is all local to you. When you read a file, you ask me. So if you read a file, I have some indication that you may be interested in that file, but I have no idea when you started to be interested in the file, how long you're going to be interested in the future, what mode you're operated on, and all those things I don't know. So that complicates some of the stuff that Spritely NFS tries to solve, and that all falls into the notion of a cache consistency model, right? Your goal is to make sure that all of you can cache something for the most part. And at some point you cannot do that, and we'll see what those are, right? Does that make sense? What do you think of the paper? Was it easy to read, or unfortunately, like many of the papers, we couldn't read the Sprite distributed file system paper, which is sort of depends on, and we didn't read the NFS paper, which is sort of depends on. But I thought they do a good job of giving a overview of what exactly NFS does, what exactly Sprite does for their perspective, right? Which ought to be enough to read this paper, right? Especially, how many of you read the NFS paper, the
other one that you put as an alternate?
Yeah. Was that useful?
I didn't think I needed to read that to understand the other paper, but it was interesting to see what Sun was doing on that.
Yeah. So how many else did you read the paper, the NFS paper? Okay.
Which one was it?
The design and implementation of the Sun NFS. They talk about stuff which have no relation to anything, right? They introduce the notion of VFS, right? Which is an important concept. Essentially, now you can build different file systems by creating a virtual file system layer, right?
Yeah.
And they had to do that because before that, file systems can be directly built on top of the hard disk because that's what they were dealing with. When you have a VFS model, I can either mount local file systems or network file systems. And they all go to this virtualization layer, so that means that I can now do whatever I want, right? I can create different kind of stuff, which sort of thing that we take for granted because many of you, if you're mounted, you don't think about network mount or local mount because all of it is sort of mount. That came with NFS, right? But that's not related to what that is an aspect which makes it easy for you to build distributed file systems. It had nothing to do with NFS, right? They had to do this if they had to do some other network file system or whatever, right? So it's good to know that the VFS came from NFS, the NFS world, but it's sort of tangential to what we are interested in the Sprite paper, right? They talk about the notion of XDR, RPC, right? Which was a big deal back then, right? So that gave portability, right? How many of you used RPC mechanisms in any language? Which ones?
We use it a lot with regard to Windows NT, and that uses the RPC mechanism an awful lot to communicate between the servers and the clients.
Yeah, and
I used it in .NET briefly to test. So.
Yeah.
I worked with some proprietary thing with the company I used to work for.
Okay.
Some Java related stuff.
But you use Java RMI, right?
Yeah. Well, right.
I mean, underlying is RMI plus some proprietary stuff.
Yeah.
Okay. So one of the things that you notice is the remote procedure call, right? I mean, remote procedure call is basically you have to send the request to another server. It does something and gets the result back to you, right? That's the remote procedure call. But in terms of what it means is you need to somehow collect all the data, all the arguments, pass it along to the other side, and then get stuff back, right? So I have no idea how they do it in Windows, right? But since they only work on x86, they can assume that all the machines have the same architecture. So they can make a RPC by essentially sending the same data, the local data structures, right? Whereas if you want it to be portable, it could be on different Indian machines. It could be on a PowerPC, or it could be a Windows or what have you. So you have to change. You have to make the representations fit any number of machines, right? So the idea here is, if I have a server running on some machine, and if you have a client running on some machine, you should be able to talk to me. In which case, we should have a common language we can talk, not the local language, because local language would mean that we both have to be the same architecture, right? So that was a big deal here. The whole Sun XPC, they gave a language which lets you specify all these parameters. Then it generates code which essentially makes it possible for you to write in your own programming language. All the arguments which are passed in the network order. It does the translation for you, and it gets back to you, right? So that was a really big deal, because that meant that when you work with NFS server, you don't have to be also running on the same kind of architecture. It can be any architecture. The NFS server can talk to anybody because it's doing the RPC, right? So that is a big deal, because if you think about any of the modern systems, that's taken for granted. I mean, you cannot imagine writing a RPC mechanism which expects, which sends integers in 32-bit little endian or whatever. You do it in the network order, right? So things which seems so natural to us was introduced through NFS. So the NFS paper would talk about those, talk about the innovation of having portable file systems, the innovation of having a VFS, so I can treat the network and the regular file system as the same, and other aspects, right? Which are well and good, and I think you should know where these things come from, but not the consistency also explained, right? So this paper ought to be enough to read through and figure out what happens, right? So NFS, this is the sort of the vanilla NFS, and NFS, the current version is NFS v4, and that has added some modifications, but I think the basic fundamentals are the same, right? The main thing is it's stateless, right? So like I said, all the requests have to go to the server. So every client, when they make a request, you have to say what you want, right? So you have to, so it doesn't remember any state. So you cannot say, I've been reading this file for a while, so you have to keep asking every time what file you want to read and where the offset, right? The server does not know anything about what you read so far. So you have to say, I want to read file blah from this byte to this byte. It's up to you to give the credentials to make sure that you can read. So if you have to prove that you are still allowed to open the file, right? And right. So what does that change? What does that? How does that affect your notion of Unix files, right? So with the NFS, if you want the NFS file system, it should look like a local file system, except it should be slower. But other than that, it should look like a regular file system, right? With the stateless model server, would you still see it like a Unix file system, or does things change?
I thought that was the whole purpose of the VFS layer, is so that way to the application it would look like just the Unix file system.
Yeah, so it looked like a file system for the most part, right? But I'm saying, does doing this stateless server in subtle ways change stuff that actually say it in the slide somewhere, but the paper actually goes through that, right? One of the things is the operate on a file that is open, right? So one of the nice things about Unix, I don't know if you use this stuff, is if you open a file, till you close it, you have a handle to the file, right? Regardless of what happens to the file by somebody else, right? Which is a model which seems sort of what you would want. So if you open a file, until you close the file, that file handler that you have is valid, regardless of if somebody else comes and deletes the file. So if you come and delete the file, you don't get an error just because somebody deleted the file. You still have your handle, right? Your handle is always valid till you close the file, That seems like the same thing to do. You open a file, you expect the file that you're opening to be available to you till you're done with it. You don't want somewhere halfway through things to fail. So they decide that's the model we should go. What that means is he can open a file, right? Unlink the file, but still have the handle and write to the file, right? So this particular file would exist in terms of your disk quota. Your disk quota will go down because you're now having this file, but the file doesn't actually exist in a namespace, right? So when you close the file, it's gone. But till you close the file, you have this file, right? So I can create a really humongous file. If I don't have disk quotas, I can create a really humongous file that no one can see, right? And when disk quotas were not there, we used to use this as a prank on the system administrators, right? So essentially you create a program which opens a file, unlink the file, create a large file, make this file system become all full, and let the process run. The processor does not do anything. You just have to keep the handler open. So as a system administrator, you suddenly notice your file system has gone to zero bytes. And if you do a DU, you don't see it. If you use any LS and all those things, you don't see it. It's being held by this process. I mean, you can find it by basically tracing down to see what processes are opening a file on the file system and all those things. But you can essentially do that, right? Has any of you used that mechanism?
None of us play pranks on the administrators.
No. As a useful tool, has anyone used that? Like they say, it's this ugly system. Yeah.
Yeah, I had some experience about that one.
Mm-hmm.
It's not exactly what you're talking about, but somewhere on the NFS, if I have a file, then somewhere I delete it. Then I will got a file handler error.
Stale file.
Yeah.
Oh,
It's still there in my space, I think, but it's not on the disk somewhere. That's the case.
Yeah, so that's a cache consistency protocol, right? We'll see that. Yeah, so so in NFS you see it as a cache consistency. So you'll get a stale file handler, right? If you're on a directory, somebody deletes a directory under you, right? When you do ls, you get a stale handler because you did a CD to some directory and you expect to be in the directory, somebody else deleted it under you. And when you try to open it, you ask the server, you say, what is this thing? And the server says, I don't know anything about it, and you get a stale handler, right? So this is on the local file. This is not with NFS, right? This is on the local thing, right? So it's an ugly kind of trick, right? I mean, ignore students playing a prank on the stuff. It is very nice because this is one way where I can create files, temporary files that I don't have to be bothered about cleaning up, right? So this way, if I have a lot of temp files, right? So if I do the sort of the way that you are taught in undergrad or whatever, you open a temporary file, you write a whole bunch of stuff, and then when you're done, you delete it, right? If your program ever crashes before you delete it, then those are left behind. So if you go to the /temp and look at the files, there are a lot of files which are left behind, which are orphaned because somebody had the intention of cleaning it up after they're done, but they never got around to do it, right? How many of you noticed on the /temp you have all these junk files, right? And one of the modern other things is you have RAM file system. You don't actually have a disk file system for /temp because of the Berkeley study which showed that most files are small and stuff. So temporary files, because of the Berkeley study and what we know, ought to be on a RAM file system, which really means that if you reboot the system, those files are gone. So one way to deal with that is to put everything into the temporary directory and then hope that it will be gone when you boot up the system. Other way to do that is to use this model, right? So if I know it's a temporary file, which if I'm not sure if I'll be around to delete it, I open the file, have a handle to it, and then unlink the file, so that if I ever crash before I finish what I'm doing, the system will take care of it, right? So it's a really fantastic tool. So a lot of applications use this model because this is a way for them to make sure that they don't have to deal with the stuff, right? That kind of messes up when you go to NFS, because NFS, you have to say it every time what you want, right? So if you have a file handle from NFS for a file, and you're operating on a file, you keep reading the file, right? If somebody deletes the file under you, NFS server does not know what's going on. All it knows is you ask for it, I give you. So if you open never goes to NFS server because NFS server does not need to know open. All it knows is you have do some operations on it, right? So when you do open, the client may ask the server to make sure that the file exists. So it will do a get attribute call to make sure the attributes are good enough for you to open. But open really is not something that the server cares about because there's nothing that is being served to the client, right? So I don't see this open. So if you do unlink, the file is gone, right? When you start to read again, you're going to come back and say, I want to read this particular file handle. The server does not know anything about file handles. All it knows is the file name, right? So if you say, I want to read that particular file block, and I look up and say, oh, that file is not there. So I have to say the file is not there, right? So it'll break the semantics that people are used to because of this weird quirk of how NFS, how the system used to work. And this is an artifact of how NFS, how the stateless stuff works. If it was stateful, then I can keep track of this. I can say, even if you did the unlink, this person was doing the stuff, so I can make this stuff. But if I don't have stateless, I cannot do that because I don't know what to do this. So your application which worked fine will no longer work. Even if you have the VFS to make sure that everything goes here, I change the semantics, right? In the Unix semantics, till you close, you have the handle to that file. Whereas here, it's stateless. So whether you like it or not, whether you believe it or not, whether whatever you do, you as an application, if you're calling open, read, close, your semantics you assumed was open to close, you had the file handle. But with the NFS model, the pure NFS model, all you end up going to have is open, and all the reads are separate. So some of the reads may fail because of these events which you didn't expect before, right? And you may see it as a stale handler or whatever you get, because at that point the file no longer exists, so your application will crash, right? So they fix it in the modern more stateful NFS by you're moving your file to .nfs. How many of you noticed this special file called .nfs something? So if you're operating on a file called like file.c, and if you delete the file, right, it internally moves it into a .nfs some hash number, and the file server will continue to behave like the traditional file system. On NFS variants where you have to, it's like a Spritely NFS variants, right, which is what we do, but you have to solve, I mean, it's still visible to the user, which is not the case with the Unix file, right? The key here is to remember why it's happening. It's not a bug, because if you have stateless, this is what you'll get, right? And the other issue is all requests are validated. In the old Unix model, if I have a file open, you can do whatever with the file. You can make it unreadable to me, but it doesn't matter because I have the file handler, a whole, right? So once I open the file, I'm allowed to read it, right? It doesn't matter what you change the permissions on, which is not true with the new model because it's stateless. So if you open the file and then I change the permissions so that he cannot read it, then those read will fail now after the thing. So your program will behave differently under NFS than it did if you were doing it on a local file system, right? So you have to be aware of this, because when you get a stale error, right, you have to sort of know what may be causing it, right? So the stale error is a generic error message, but essentially this is what happens. Whatever you thought you could do, you can no longer do because it's stateless. The server has no way of knowing what changed. And you change something, and the server cannot help you with the more good answer about, what really happened was this. All you can say is, I don't know, I mean, what you're asking no longer exists, right? It's up to the client to deal with that, right? So the consequence of having the stateless server is the server knows nothing about it, which means the clients have to know everything about the system, right? The server has no idea how many people are concurrently operating on the file, right? Which means that the clients have to do write through, right? Which means that you're allowed to cache read contents. We'll see how long and all those things a little bit. You're allowed to keep contents that you use for reading, but all writes have to be written through to the server, right? So any write you do will have to go to the server. The server it's free to not write to the disk. It can do whatever, right? So the server cache could capture those and not having to go to the actual hard disk. But every write you do has to be written through to the server cache. Why is that? Can you delay this write? Can you delay some of the write not to be write through on the client?
If you do that and the client crashes, then you lose
Mhm.
everything that was in the cache.
Mhm.
And so the user might think that it's been written,
Mhm.
because to them it looks like it's been written, but
Mhm.
if the client, but then it hasn't been.
Yes, that's one of the, yeah. So yeah, you change semantics because you thought the write went through, but the write is gone because the client went away, right? What other problem can happen when you have the write, if you don't have write through policy in NFS? I didn't say that up here, but
Cache consistency is an issue with other clients
Mhm.
going at the same file, because you would have written to the file, but it would never be showing up on the server.
Mhm.
And so Nathan trying to get at the same file from a different client wouldn't even know that I written.
yes,
to it.
if somebody else is reading the file, they won't get the new blocks because that I haven't gotten it, right? So till you tell me, I have no way of knowing what's going on. So if you delay it and you don't do a write through, then I won't know it. So somebody else would get the older, staler content. So you have to do a write through, right? Which is the reason why the NFS is good because it's stateless, right? That means the system is very easy to build. And how many of you have seen what happens when NFS server dies? What do you think will happen if a server dies? You're operating on a client and then the server dies. What do you think should happen? Obviously you can't use a server, but what should happen to the client?
Sysadmin should be fired.
Why?
It's his job to make the servers run.
But what do you expect would otherwise happen for the client?
If he's writing, then he should be able to just kind of buffer the writes until the server comes back, and then he should be able to tell the server, I was writing this file, and here's the bytes that I want to write. And if he was reading, he should be able to say, server, I was reading, did somebody make an update to the writes, like the cache?
Yeah. So, but the bottom line is, you won't be able to do anything while the server is down, but when the server comes back up, you'll be back to business. It's as if nothing really happened, right? So, if you ever worked on an NFS file server which is mounted the way I mentioned, if you do ls on the directory, then it'll just freeze because it's waiting for the server to come back. When the server comes back, everything will be fine, right? You wouldn't notice anything going wrong because there's nothing really. I mean, all the state is on the client, right? So it knows that you're asking for ls for the directory. It'll wait till the server comes back and it'll be fine, right? It's not necessarily true for all the cases, but here that's the case. That's the nice thing with the systems, especially when the servers crash a lot. Especially if you're using lots of servers, if a particular server is down, you wait till it comes back, and now you can actually do if you who would tried NFS, you can say soft interrupt, which means that it'll come back, it'll give a fail, it'll fail if you try to do ls on a directory which is not, the server is not there. If you do a hard mount, then it'll just wait, right? But regardless, your client can continue to do other stuff that doesn't depend on the file system because all the state is on the client, right? Which is not necessarily true for all the cases, right? Yeah, so the other thing is NFS does block cache, not the file level cache, right? And the choice here is not so cut and dry. Depends on what you're trying to do, right? AFS traditionally is full file cache because of other reasons, right? AFS is last writer wins protocol. We'll see what that is in the next lecture. So that makes it that even if you do a block level cache, the consistency model only kicks in when you close the file, right? So it doesn't matter whether you do a block level cache, file level cache is good enough, right? What's the reason why you wouldn't want whole file cache?
If you have a log file, for instance, that only gets appended to, then it doesn't make sense to have a full file cache because you don't want the whole file invalidated just because somebody appended something to the log if somebody's reading from the beginning of the log, for instance. So you would just want to have a block level cache because then only the end of the file, when only the end of the file is changed, then if somebody's reading the beginning of the file, it doesn't really matter.
Depending on how the consistency, right? So AFS does not have the problem, but in general, that's one of the problem, right? What's the other problem against having a whole file cache?
Large files?
Yeah, large files, right? Whole file cache means that unless you're able to do something with that file, either in memory buffers or in local disk, you cannot open the file, right? So if you have a 1 terabyte file that you have a server to store, but if you're doing whole file caching, then you can't cache the file. I mean, makes sense, right? So traditional AFS was doing whole file cache, right? Which means that all the file will have to be cached on your local system, right? Which means that you can only open files which are as big as what your local storage is. So it's possible that on some clients you cannot open the file, on other clients you can open the file, because it depends on the whole, whether you bring the whole file, right? So what is the positives of having a whole file cache over block level cache? Ignore NFS in details, but in general, right? The problems with the whole file cache is you cannot cache anything which is larger than what you have local space for. What is good about whole file cache as opposed to block level cache in general? Yeah.
Because you're likely to access, because most file access the whole file sequentially, then you can be, if you load the whole file, then you only have to do one, well, not exactly one disk access, but you don't have to keep going back to the disk over and over again to read the whole file. You can get it all at the beginning.
Yeah, actually, I think, yes, in this kind of context, you don't have to go back to the server all the time, right? Not let's say to the disk, right? So the server can do whatever. It can either read the whole thing into cache or whatever, but from the client, you don't have to keep going all the time. So if you do a block level cache, if I have a long file, I have to kind of issue requests to get each of them, right? Whichever way I do, right? So if users typically only operate on certain blocks, right? If the users typically only operate on the 10th block of a file, then block level cache would be a good idea, because you only need to cache one block. So why bother to bring the whole thing, right? The whole file caching means that you bring the whole file. If you're not going to use all the stuff, then it's not a good idea, right? And again, this is where you tie the Berkeley paper on what happens, right? So we knew that people typically open the file and read the whole stuff. So if you're going to read the whole file every time, I'm caching because I expect you to reuse it again, right? So if you're going to reuse the same file over and over again, then it makes sense to do a whole file cache, right? Whereas with the block cache, I lose that, right? And so in typical Unix, like we said, the user reads the whole file. So actually, whole file is not such a bad idea, right? And you may notice it in some sense, right? So we haven't read the AFS yet, but you would have noticed that in AFS, if you go to a new machine that you've never been before, you log in, you look at the file, it'll be very slow, right? Because it's pulling all the stuff locally, right? Once it's pulled all the stuff, it'll actually be as fast as the local file system, because everything else after that, as long as the cache validation protocol is working, as long as there's no reason for something to be invalidated, right? So if you're the only one who's operating on a file, there's no cache invalidation anywhere, then AFS degenerates to a local file system after you've used the system, right? You won't get the benefit here because you're only looking at blocks, so you may not see the whole file system stuff, right? So that's an important trade-off that you have to realize between this and AFS and how that helps, right? And error recovery in here is easy, right? Why is error recovery here easy on the stateless file system?
Because when you bring the system up, the file is there. I mean, you've already done write-through from all the clients. And so, like you say, when well, basically, if the server crashes, when it comes back up, the file's there. If a client crashes, you don't lose anything because everything's been written through.
Yeah, and also the server does not, when the server comes back up, it doesn't have to do anything. It just knows that any new request will ask all the stuff it needs to ask, so it does not have to do anything special, right? And if the client dies, it forgets all the stuff, and so be the case, right? And as you'll see, the Spritely NFS, they had to change it to not a stateless server but a stateful server, which means that the server now has to keep track of some state, which means that if somebody dies, the server has to keep track of something, right? And one of the important aspects that they mention is the real problem with that approach is not the recovery itself, but the aspect of making sure that somebody really died, right? Which is not maybe what you had expected, right? The real challenge is the server has to now keep track of all the clients, right? It has to make sure that the client did not die, right? And when you build distributed systems, that's one of the hardest things to do, which is make sure that somebody is dead, right? So from a server perspective, a client is dead. When is the client dead?
I mean, that's the problem. I mean, is it because the network has died? Is it because the client has died? Is it just poor response time on the network? I mean, you can't really tell for sure when the client.
But that's one of the fundamental things about all the system, right? So I need to know why. So I can define dead as if I'm not able to communicate with you, right? The other way is if the client comes back and says I'm dead, right? If I send a message saying I'm dead, that's trivial, and you can do that if you're shutting down the machine. Before the last thing you can say is, here's I'm going to go away. So that's fine, right? But that's not what we worry about. I mean, we worry about the case where the client goes away otherwise. So the client may still be alive, and I may not be hearing it because network is dead, not on the client, not on the server, but somewhere in the middle. It may be so slow that so whatever timeout I have to figure out what is happening may not be kicking in fast enough, right? So, but there's always like weird cases where things break down, right? So I may have a timeout. I may say, if I don't hear from you for half an hour, I have to assume that you're dead, right? It sounds like it's a long duration, but sometime or other that will happen, right? And the problem is, if I think that you're dead, I have to do certain things to, it goes into the screensaver mode. So if I think that you're dead, I have to do the stuff to take away all the caches from you, even though you're still alive. So when you come back, you're assuming that I'm in a certain state. I'm assuming you're in a certain state. So we get off kilter here because I don't know what you're doing. You don't know what I'm doing. We have to deal with those, and that's pretty messy, right? That's a general problem with all the distributed systems. It's a lot easier to assume that I know when somebody has left the system, but in practice, you never know when somebody has left the system. So you get into this weird state where both of you are alive, but they're not able to communicate for a little bit. So when you come back, you get an inconsistent state. And Spritely NFS has the same issue. And they cannot live with that, right? So one of the subtext that they don't mention here is, do you know what's the history of how NFS was designed and what setup they were designed for? Is it designed for a wide area setting? What kind of a scale do you think NFS could possibly support? Tens, hundreds, thousands, millions of clients? Yeah.
It's meant for a small number of clients. I mean, people just basically who are accessing the same files, but not necessarily at the same time. On like a small network, kind of work group type of thing.
So NFS was designed for like a small work group of 10 to 20 people in the same LAN kind of stuff, right? It's not designed for this scenario that I talked about. It's not designed for scenarios where the network is I'm really far from the server, but I have to worry about the case where the client is up, but I don't know this kind of thing. It's sort of in the thing, right? So where does it manifest as? Where are the points where having a local LAN? Yeah.
Can I say something? I mean, you were saying before how if you can have inconsistent state where the client was actually up, but the server thought it wasn't up, right? Mm-hmm. Wouldn't the client know that it hasn't talked to the server in half an hour, mm-hmm. so it should revert to the state where it loses everything?
So the problem here is the time, right? The 30 seconds or whatever that you use, right? So you can either get into a case where you lose all the benefits of caching because you prematurely flushed all the stuff, right? And I have to make sure that you and I have the same clock, same time. So it can be correct, but lose all the benefits, right? If you haven't talked to server in some time, you may prematurely decide that all the stuff that you've done has to be flushed or something, right?
Well, what I'm saying is if there's high network congestion, right? Mm-hmm. And you were working on a file, and you haven't talked to the server in half an hour. Mm-hmm. And you realize, well, there's really bad network congestion, so the server is going to go into recovery mode. So I should assume that and ask the server if that's what happens.
So, we're not going to the networking and real distributed systems aspects of it, right? So, clients cannot reliably know that the network is congested, right? They only know there's something.
They haven't talked to the server.
Yeah, they know. So and they don't know the time, right? Half an hour seems like an obvious time, right? I mean, nobody's going to build a file server which is half an hour, but you have smaller time, right? So if you assume 30 seconds, right? You haven't talked to server for 30 seconds, it may be a good heuristic, but in a particular case, it may be an awful thing. So there's always a possibility that like you happen at 31 seconds away from me for some reason. So we go through this stuff. So I think the system will continue to work. It just have lots of hiccups in that scenario, right? But it'll just be, it's not what you want, right? You want it to be either assuming that it's going to be no caching. You don't want the state where it's half caching and all those things, right? So going back to that stuff, right? So NFS does two things. One is stateless server, right? And the other is the, what did I say? So for stateless server, right? Stateless server means that, would stateless server mean that the server is scalable? Does the fact that you have stateless server mean that I can scale to a large number?
Technically should be infinite.
Yeah, so because I don't know anything about you guys, right? So why would so can you scale NFS to as campus wide? Yeah.
I'm saying it's scalable to the point of the hardware on that NFS server can support clients. I mean, it's more efficient than a stateful NFS server on the same hardware, but it's not scalable in the sense of you only have one disk system where you're going to get the throughput from the disk if you scale infinite number of users. Let's say the hardware can support 1,000 users, right? So do you think NFS can support 1,000 users? I didn't actually quite define what the hardware supporting 1,000 users is.
Well, on a stateful server, you're potentially going to have to do more work per connection because you have to validate the user every single time that they want to do something.
Mm-hmm.
So that's going to take time, whatever time means.
Mm-hmm.
So since something takes time, you can't scale infinitely.
Mm-hmm.
If it was instantaneous, then okay, you can do it infinitely many of them. But
so one of the problems is like all the updates have to be validated, right? Like so, like I can't just assume that. I mean, so I have to do more work, right? So I have to reduce. Let's say if I can do 1,000 something, but since I have to validate and validate has some cost, let's say I bring it down to 900 or so, right? In terms of the cache consistency protocol, is there something there that would make the server not scale to a number that it could? Because the one aspect is it doesn't maintain any state, right? What about the write through?
Well, yeah, that's what Nathan, I think, is addressing there. I mean, you can only handle so many clients writing to you simultaneously. And at a certain point, the server won't be able to process those.
Yeah, but I think it's more specifically to write through, right? If you didn't have write through, then that's how I wanted to be careful on what the number of users, right? So if you are writing to a file, all the writes have to come to me, right? So even though it's 1,000 users, if you use a different model where you're able to cache some of the writes, right? So then you will kind of amortize the cost across multiple times. So 1,000 users can cache it for a little bit and then send it to me at certain points, right? Whereas with the NFS model, all the writes have to go to me directly immediately, right? So I have to be able. So if I can only support 1,000 people, I have to be able to support 1,000 simultaneously operating users. I don't have the benefit of you having a cache to capture some of your stuff. So all the writes have to come to me, and that's the one which kills NFS, right? NFS by itself, the stateless would mean that I can go as fast as I want, but if I can't turn around, so if I cannot use the client caches and everything has to come to me, right? Then I fail, right? The other aspect, so that's for write, right? So if all of you started to write, then you have to send the write directly to me. So I need to be able to do all the writes as a write-through model. So I become the bottleneck, right? So what about reads, right? We didn't say that so far, but if you have a file open for write and he has a file open for read, right? With the NFS model, I don't know who has done what, right? So you open the file for writing, you do a write through, right? NFS allows you to have a client cache, right? Because that's the least you can do, especially if you're doing read-only file, right? So if you're doing a read-only file, he's doing read-only file. He's doing a read-only file of this file. He reads it, he caches it, right? How do I tell him that you modified the file?
You can't, because you don't know who he is.
Yeah. So how could I? What are the possibilities of how I can deal with this? Forget NFS. What are the possibilities of how you can build the system, where he's modifying something, I'm knowing it, he's reading some file, I don't know what he's doing, right? So what are the possibilities I can do? Yeah.
You could pass the message to the server in some way, or you could initially have a list of all the nodes, and then as you open or update closed files, you could pass those messages around.
So I have to notify you somewhere, which is what Spritely NFS does, but in the pure model, I don't know, right? So I can't really pass anything around. I can broadcast to everybody, but you don't know, right? Yes, there's.
So you have a timeout, right? Like when you read something, after like period of time, like 30 seconds, you ask the server, like asking somebody to modify my files.
Yeah.
My cache is still valid. If not, then you recache it.
So you poll, right? You keep polling me to say what can I keep it, right? So you're protecting yourself from the notion that he may be modifying something. Since I have no way of telling you if something happens, you poll, right? And you guys should be, I think you guys are talking about it on the your first project, right? Jen and project partner is not here, but right? It does a synchronization, right? In terms of polling, right? So what do you expect would happen when you have to do this polling? Yeah, so here, like if you have something read cached, right? You have to poll the server to make sure that your what you have cached is still valid, right? So
You just need to poll with a certain frequency
Mhm.
and until it completes.
yeah, so how would you choose this frequency? Do you want this frequency to be small or large?
It would be better if it's small.
So why would it be better if it's small?
If the frequency is too large, that will increase the time that is wasted time.
And in this case, if you keep the duration very long, then you can potentially have a stale cached copy for a long time, right? So if I keep it for hour, that means the whole world would have changed the file for hour. You still get our old data, right? What's the flip side of it? What happens if you make it small? Yeah.
So it increases the overhead. You keep continuing the polling. Maybe a lot of them is not required.
Yeah. So you keep increasing the overhead to the server, not to you, right? You're doing a denial of service attack on me, right? Basically, right? You decide that 1 second is good for you, but if all of you decided to do that, you're basically asking me every second, did something change? I have to say, no change, right? The worst part is, I have no idea what's happening. So I can't really tell you that don't bother me because no one else has done any write on it, right? Opened it on write mode, right? Since I don't know what mode people are operating the files on, I may optimize and say, I saw somebody write to this file, so it's possible that they would write to the file. But even I can't do that because I don't know when they close the file, right? So I have no way of telling you anything more because as a server, I have no idea what's going on, right? So if you open a file, if two people open a file, or even if one person opened a file, you have to keep asking me whether the stuff is valid, because it's possible that somebody else opened the file in write mode, right? So going back to the Berkeley study, right? How likely are people to modify the same file simultaneously?
Very unlikely.
Does that mean that you can optimize and do something about it? It's very unlikely, right? The Berkeley study said it's very unlikely. Let's say it's 1 in a million chance, right? Does that mean you can build your read clients who are doing good, because who are capturing all the, who are not asking me for all the stuff? You're keeping a local cache, right?
Seems like the best way to do that would be to have the client read the entire file, cache it, do whatever work that they want to do, and then after they're done, since they're probably going to have it open for a short period of time, because that was also part of the Berkeley study, they then go and ask if it actually changed between the time they started and the time they ended, and if it did, then they just do it all over again.
That you need a speculator,
Yeah.
the paper we didn't read last week, right? But since we didn't have speculator back then, That's a good, I mean, that's a different system, not NFS, right? So you don't know. So you have to keep asking me. So even if, so the Berkeley study said this will never happen, or this will happen very rarely. Regardless, NFS has to be designed for that eventuality, right? Which means that you will all be asking me whether the cached copy is still valid, even though most of the time I'm going to say, no, didn't change, right? So that one aspect, it's completely counterintuitive to what the people observed. That's an artifact of how the stateless works, because if I'm stateless, I have no idea what's going on. So you have to keep asking me. So even though I could scale on one aspect, which is I can, I don't have to maintain state. Now I have to pay the price for you nagging me all the time, because you have to say, I have all the, so the more cache you have, the more you have to ask me whether all the blocks are valid, right? And I cannot keep any state, so I cannot even say it's still the same. I have to still look back and say what changed, right? So those are the important stuff to know, to take away from NFS. NFS is good in some sense. It's stateless, so that makes recovery faster. But in terms of performance, you kill it because all the writes have to go through to the server. So any write, you pay the penalty by, you pay the cost of network overhead. So NFS writes are really poor. So any of you done test on NFS writes, you'll notice that NFS writes are poor. Unless you change the, I mean, there are modern variants of NFS which kind of fudge these things, and Spritely is one of those, and the stuff, right? But in a pure NFS, if you do all the stuff, your write will be slow because writes have to go all the way to me, because so now you write it, you send a network message to me, and once I get the response back saying I got it, then you can proceed, right? If I'm a good server, I can cache it locally or send it to a disk or whatever. I can do whatever I want. So that's one of the reasons NFS cannot really scale, even though you expect it to scale well, right? So the key to remember from this is, if you want to develop a protocol which is scalable, you better make sure that you don't nag me so often, right? You shouldn't have to ask me all the time. One of the ways that they do is, you tell me what you're doing through the open call, the Spritely NFS, then I'll tell you back when something's changed. So if I don't do a callback, then that means you can keep your cache. So I don't have to ask this stuff. So I can scale to a larger extent, right? So one of the other things it's annoying when people complain about NFS having poor performance. I'm not saying somebody from this project, this group, but in general, people complain that NFS is something, right? It's important to understand that NFS is something because of the decisions that are made, and decisions have certain consequences, right? So you cannot complain that I'm asking, there's lots of cache validation messages, right? Because that's fundamental to how the system works, right? If I wanted, how do you eliminate all the cache validation messages? What's one way you can have no cache invalidation messages? Or the request to say, is my cache still valid, right? What's one way to go there?
Deny any request to, well, I guess you can't do that. You have to keep state about who has the file open.
Yeah, that's one way. Actually, the other one would work too.
But how would you deny a request for a block that was asked for?
No, I said I can deny cache, right? I can say don't cache anything, right? I can solve it by saying none of you should cache anything. You should always ask me, right? So that'll solve that problem. It'll kill me on the other side because I need to send everything to you, right? So, the point is it's not a bug, right? It's a feature because it's the trade-off, and we have to understand what the trade-off is. So if you're building a file system using NFS, you have to understand those. So if you're using NFS on the lab, you need to know what it is, right? And I wish I can keep this, make it remember the state. Right. So the Sprite, which we did the paper, the Sprite distributed file system, which they talk about, is a stateful server, right? So it knows state, and so you get all the benefits of knowing state. So now I know who's opening. So I need to know who's opening a file. So it's not okay like before to not know about opens. So every state open I need to know, every close I need to know, right? Why would I need to know when you closed a file? Right? Why is there a need to know when somebody closed a file?
is the state keeps track of who's accessing the file, either read or write. So
Mhm.
it's got to know when it can release that, otherwise.
Yeah, so otherwise, yeah. Yeah, so if I know that you're no longer writing the file, then I can go into a mode where I can be more liberal with caches, right? So